Hello, beautiful people, and welcome to the AP Chemistry exam free response question number 1 from the 2025 administration. In this video, we're going to run through the answers and solutions to this FRQ and see what was intended by all of them. Now, in my class, we call this a postmortem because we're kind of going over things. It's kind of a chess term, actually. After the king is dead, you go through the postmortem and find out how you could have improved. And some people don't like them just because you see your mistakes. But also, I think it's a good learning tool to learn from our mistakes and be prepared for the next time we see questions like this. So I hope you're excited about that. And if you're here, maybe you took the AP exam and have some personal history with this question. So let's get into it. And if all goes according to plan, in a couple minutes, you'll be ready to do this next time. All right, let's get started with question number 1, part A. And I've already worked out the solution, so this is going to go pretty quickly. We won't do any pause the video moments in this episode because you have probably already done this on your own at the AP Chemistry exam. So the first question was about a mass spectrum for magnesium. And it says an incomplete mass spectrum for magnesium is shown in the diagram. The percent abundance of magnesium 24 is 79%. The percent abundances of the other two are magnesium 25 and magnesium 26 are approximately equal. Complete the mass spectrum in part A by drawing thick lines on the appropriate locations to represent the percent abundances of magnesium 25 and magnesium 26. So right off the bat, we're supposed to remember our atomic structure and that isotopes of elements exist in which they have the same number of protons but different numbers of neutrons. And the relative amounts of them are kind of random. You can't really predict what they're going to be. You have to rely on a mass spectrum like this one. And so we're going to sketch the two peaks for 25 and 26, but we're also going to describe the difference in atomic structure that accounts for the difference in mass between magnesium 25 and magnesium 26. So here's what I've written on here. All right, so I sketched two that are relatively the same. So we're almost at 80, and so we have another 20 to go to get up to the 100% of all three isotopes. So I put them right around 10% or 11% each. I'm sure there's a little range that they'll accept for those two peaks, but they should be approximately the same and right around 10 or 11, just to make up that difference. And for part 2, both of the isotopes, magnesium 25 and magnesium 26, contain 12 protons. It's nice to share that with your reader so that they know that you know what's going on. Or as I like to say, they know that you know that they know that you know what's going on. But magnesium 25 contains 13 neutrons, while magnesium 26 contains 14 neutrons. All right. Second question, part B. A student prepares a 1.85 times 10 to the minus third molar solution of magnesium nitrate in beaker 1 and a 2.8 times 10 to the minus fourth moles per liter solution of NaOH in beaker 2 as shown. This is the diagram they gave. The particle diagram shown represents a magnesium ion, Mg2 plus in beaker 1. A sodium ion, Na plus in beaker 2, has a weaker attraction to water than the magnesium ion does. Explain this phenomenon using Coulomb's law and each of the following. There's two parts here. The first part, the relative charge of the ions. And I wrote it this way. Coulomb's law states that the ion dipole attractions are greater with greater charge on the ion. The higher the charge, the more it can pull water molecules close to it. Magnesium 2 plus has a 2 plus 2 charge, while sodium has a plus 1 charge. Therefore, sodium has a weaker attraction. Now let's check out the next part, going back to the original problem. Now we got to talk about the relative radii of the ions. Okay? So think about that for a second if you'd like. And what I have here is that Coulomb's law, I also like to refer to the law in the question when I'm crafting my answers, also states that the ion dipole attractions are greater with lesser radii, as the ion and the water molecules will have a shorter distance between them. So Coulomb's law says the energy of the attraction is proportional to the charges on the ions, or ion, and inversely proportional to the distance between them that they get to. So sodium has a larger in size than magnesium 2 plus, and so it will have a weaker attraction. So that's the two parts of Coulomb's law. And then in the third part of letter B, or it's actually now C, we need to calculate the pH of the solution in beaker 2. So the solution in beaker 2 is a sodium hydroxide solution, 2.8 times 10 to the minus 4 moles per liter. I'm not going to be able to get the pH directly, but I can get the pOH pretty quickly. Because sodium hydroxide is a strong electrolyte, and we needed to know that, it will dissolve completely, so the concentration of the OH ion is 2.8 times 10 to the minus 4th. So that's good to know. Then the pOH is simply the negative log of that, 2.8 times 10 to the minus 4th. I punched my calculator and I got 3.55, 2 decimal places on the pH. And then subtracting the pOH from 14 gives you the pH. So pH plus pOH equals 14. Subtracting that from 14 gives me 10.45. Okay, now we're kind of moving through a sequence of things. They like to do this. Now we're going to take solution A and solution B and dump them together. So we've got beaker 1, beaker 2, and here's beaker 3 where they're both going to go. Okay, we need to calculate the magnesium after the two solutions are combined, but before any reaction takes place. Assume the volumes are additive. So here what we need to do is say, all right, here's the concentration of magnesium in 35 milliliters. But the moment I mix them, it becomes 85 milliliters. 35 plus 50 is 85. And it will immediately get diluted to some new lesser molarity. And that's what I need to find out. Once I recognize that it's a dilution, I didn't have a lot of space here, but I went over here and said, all right, M1V1 equals the molarity and volume at the time 2. So molarity times volume gives you moles. Moles stays constant. We're just adding water. So the molarity goes down if the volume goes up. So here's my initial concentration, 35 mils. I didn't have to change that into liters because the mils are going to cancel anyway. Times the new molarity at 85. And the new molarity I calculated is 7.6 times 10 to the minus 4th moles per liter. And since I had room here, I said down here we're going to write the expression for the solubility product constant KSP. We're not calculating anything here. We're just writing the expression, which is KSP equals magnesium 2 plus the OH minus ion squared, because when it dissolves, there's going to be 2 OHs for every mg. All right. And we're not going to put the solid on the bottom. The solid magnesium hydroxide is not going to be there because it's a solid. Okay, now we're still in this region where we're talking about these beakers being mixed. After the two solutions are combined in beaker 3, but before any reaction takes place, the OH concentration is 1.65 times 10 to the minus 4th. Using your answer to part B, calculate the value of the reaction quotient, Q. And when I plug in my current values, that's what a reaction quotient is. We're plugging in what we know. We just calculated 7.6 times 10 to the minus 4th. And we're told that the OH concentration is 1.65 times 10 to the minus 4th, and we have to square that in the equilibrium constant expression. Okay, and I got 2.07 times 10 to the minus 11. Now I know a common error that probably occurred here, and that is when you're doing KSP problems like this, and if you ever did an ice table, what you would end up putting in your expression is x and then probably a 2x squared. Okay, and a common mistake would be to double that concentration that they gave us. But what we have to understand is that they came from a separate beaker, and they didn't actually come from the redissolving of the magnesium hydroxide. They are independent of the place that they came from. And so the whole concentration is 1.65 times 10 to the minus 4th, which is essentially equal to whatever 2x might have been had it been dissolved. But we don't have to double that, so kind of make a note of that. But we do have to square it because it's part of the expression, and I got a Q value of 2.07 times 10 to the minus 11. And then the last part of that is to say, all right, using the reaction quotient Q, predict whether a precipitate should form as the mixture in beaker 3 approaches equilibrium, and then justify your answer. To find out if a precipitate is going to occur, you need to compare the Q to the K value, okay? And maybe you recall doing this. But in my case, my Q value was higher than the K value. The K value is 5.61 times 10 to the minus 12. And we got this, which is 10 to the minus 11th, which is bigger. So I said, yes, a precipitate will form because Q, the current concentrations of the ions, is higher than KSP and is going to facilitate some precipitation. And then we get to this last question, which validates, I think, what I came up with. In a separate experiment, the student adds HNO3 to decrease the pH of a saturated solution containing an undissolved magnesium hydroxide. Does the amount of undissolved MgOH2 increase, decrease, or remain the same as the HNO3 is added? And we have to justify our answer as we usually do. It doesn't tell us with a calculation or anything like that. I did provide a quick little couple of chemical equations. So according to Le Chatelier's principle, the amount of undissolved magnesium hydroxide will decrease. Okay, and why? Well, I said the equilibrium is MgOH2 is trying to dissolve to make magnesium and 2 hydroxide ions, right? And it's going to set up an equilibrium with itself doing that. There's going to be some solid at the bottom according to their description. But adding hydrogen in the form of that nitric acid reacts with the OH, removing it from solution. It basically is taking a product away from this equilibrium. And so more is going to want to dissolve to take its place, leaving less of the MgOH2 solid as in the bottom of the beaker. So I said it would shift to the right and use up some of that magnesium hydroxide. Okay, so there were all the parts of the FRQ number 1 from 2025. I hope you found it helpful and enlightening to look back on your work or think about your AP exam. We will keep doing some more of these in the coming days, and I hope you find them helpful. And in the meantime, happy studying, have a great summer, and have a great day.